Alright, welcome back Gen Chem 1 students. Today we are going to be starting Chapter 11. Chapter 11 is on intermolecular forces. Alright, so the intermolecular forces which I will abbreviate in my notes as IMF in the future. But the intermolecular forces, these are attractive forces that exist between particles. And remember, particles, this is our generic for atoms, ions, or compounds. Alright, so attractive forces that exist between particles. This is the second part of the story that I started when we were talking about why shape is so important. Molecules, reactions, all chemical processes, all biological processes, it all boils down to, are these molecules, do they fit together like puzzle pieces? That was last chapter. And then, are they attracted? That's this chapter. And how are they attracted? So the structure and function of molecules, of reactions, of all biochemistry, from conception of life through every process, every disease, every interaction, it all is really governed by these two ideas, the shape and the attraction. And so you'll notice actually that I skipped chapter 10 because that doesn't fit the story right now. Chapter 10 is covered later in Gen Chem 2. But back to intermolecular forces. A couple notes on it. This exists between the liquids and solids. IMFs not present in gases in the gas phase. Molecules are too far apart. Their attraction relative to the kinetic energy of the motion of the particles is irrelevant. But in liquids and solids, these particles are close enough that they influence each other, that they attract one another. And this actually changes boiling points, melting points, and all a host of physical properties of molecules is directly related to intermolecular forces. Now, there are a number of types of intermolecular forces. So the first one I'm going to go through is probably the easiest to understand. It is the dipole-dipole IMF. Alright, so a dipole is a polar molecule. So let's draw a generic molecule, and we'll say this end is a partially positive end and this end is partially negative. Alright, so they have to be polar molecules. And because there's this permanent uneven distribution of electrons within these polar molecules, opposites attract. And so the there's an attractive force between the two molecules. That is the dipole-dipole intermolecular force. So that type of intermolecular force, that's pretty easy to understand. We've got these charged regions on molecules that line up with one another, opposite charges aligning, and that's creates this intermolecular force. Now, the stronger the polarity of the molecule, the stronger the intermolecular force. Now, there's another type of intermolecular force that would be called the induced dipole. Induced dipole. Alright, now the induced dipole, this is nonpolar. Well, actually the induced dipole effect is present in all molecules. It is just the most important in nonpolar. Alright, so let's take a particle. Has an even distribution of electrons. I'm going to just draw some electrons in here. I'll draw 4 electrons in. Alright, so this is nonpolar. Now, in this electron cloud, and think in your mind, you should have the model of the electron cloud. Alright, and now remember, electrons are constantly in motion. So in one brief instance, perhaps there's an uneven distribution of electrons. In this instant, in this snapshot, there would be a weak negative charge on one side of the molecule and a weak positive charge on the other end. We would have created a dipole very, very temporarily and usually a bit weaker. However, if there was a molecule next to it, each one of those electrons will get pulled towards the positive charge in the neighboring molecule. That would pull its electrons over, and very temporarily we would set up a weak attraction because of the positive and the partially negative on those respective molecules would set up an attractive force. But because these electrons are still moving, they're going to go back. So it is a temporary, a very short-lived force that gets created. Okay. Now, this induced dipole force, while it is weak, some molecules, the electrons are more easily distorted than other molecules. So let's take some real-world example. Let's look at a series of compounds. Alright, so let's look at fluorine, chlorine, bromine, and iodine. And these are all the diatomic, or this is 4 of the diatomic elements in the halogens. They have, well, next let me pull up their boiling points. Alright, so 85 Kelvin. It boils at 85 Kelvin. Remember, room temperature is 298. So, fluorine is a gas at room temperature. It's already boiled. It boiled down at 85. We look at chlorine gas. Chlorine boils at 239, so still well below zero. So it is a gas at room temperature. Now, bromine has a boiling point of 332 Kelvin. So that's above room temperature. So bromine is a liquid at room temperature. And then finally, iodine boils at 458 Kelvin. That is a solid at room temperature. So I was just talking about the strength of these induced dipoles. Why did I look at boiling point? Well, let's take a quick thought about, let's draw some molecules. They're in a liquid, and these molecules are attracted to all of their neighbors, right? So we get this network of intermolecular forces that exist between molecules. Now, if I want to turn them into a gas phase, I have to separate them. Well, in order to separate them, I need to break all of the intermolecular forces holding them in place as a liquid. The stronger the bonds to your neighbors, the more energy it takes to boil. So, as the boiling point increases as I go down this table, I know so does IMF strength. The strength of the IMFs in iodine are far greater than those in fluorine. Alright, so if the intermolecular force is increasing, that means I can distort my electrons easier in iodine and then fluorine. Well, this distortion is a property, is called polarizability. This is the ability to distort the electron cloud so iodine is more polarizable. You can distort its electrons more, create a stronger attraction between neighboring iodine molecules. And why are some compounds easier to push their electrons? Well, let's think about it. Iodine is all the way at the bottom, That's element number 53 versus element 9. It's much more massive. It's much larger. And so polarizability increases with the size / the molecular weight. The bigger the compound, the bigger the element, the easier it is to distort those electrons and push them around. Alright, now the next intermolecular force, the type that we want to talk about, is a very special one. The hydrogen bond. Alright, so now the hydrogen bond, this is a specialized dipole-dipole. It is only created when hydrogen is bonded to nitrogen, oxygen, or fluorine. Alright, those are the bonds that must exist. H to N, H to O, or H to F. Now, this is looking at the molecule. This is not the intermolecular force yet. When I talk about the hydrogen bond intermolecular force, it's to another molecule. Right now I'm looking at how it's created. So if you think about these three elements, these three are the most electronegative elements on the periodic table. Remember from a chapter or so ago, electronegativity is the ability to pull electrons towards itself in a covalent bond. So in each one of these bonds, H to N, H to O, H to F, the electrons are being pulled, the shared electrons are being pulled towards the electronegative element. Well, hydrogen starts with one proton plus one electron. So if you only start with one electron, you go to share electrons and the atom you bond with pulls them away from you. You're left with just your proton sitting there. And that's what happens. And so you have a very strong IMF created. So if we think about water, water, as we know, is the tetrahedral electron geometry, bent molecular geometry. We know that we have two sets of lone pairs on oxygen. And then we know because of electronegativity, these shared electrons are being pulled closer to oxygen. So now we create our small negative region on oxygen, and then our small positive regions on hydrogen. The hydrogen bond intermolecular force, again, opposites attract. So right here in green, that is your hydrogen bond intermolecular force. The force created between the molecules because of this strong dipole. So these bonds are unusually strong. In fact, if you were to use the periodic table to predict the boiling point of water, you would predict that the boiling point of water would be something close to, say, minus 75, minus 80 degrees, that ballpark. Well, we know that's not true. It boils at 100 degrees, significantly higher than what we would have predicted based on just the periodic table, because the periodic table does not predict this unusually strong intermolecular force. Remember we said the stronger the force, the higher the boiling point? So water, because it forms these really strong bonds to its neighbor, is a liquid at room temperature. That is actually quite unusual. All the other small covalent compounds, carbon dioxide, hydrogen disulfide, any small covalent compounds are gases at room temperature. It's only because of these really strong intermolecular forces that allow water to be a liquid. Now, there's one other critical spot for a hydrogen bond, and that is DNA. Right? The two strands of DNA are the base pairs, right? C to G and A to T. Those base pairs that you learn about in biology, they don't know that adenine goes to thymine. There's no molecular intelligence. There is no such thing as atomic or molecular intelligence. The reason that they go together, those base pairs, C to G and A to T, is because they fit together. That was last chapter. The shape of the molecules allow them to interact. That's step one. Step two, they're attracted. They're attracted by the hydrogen bonding. The reason they don't cross and bond to other base pairs, they're not the right shape and they're not attracted. Simple as that. And when you think about DNA, in order to undergo replication, you need to pull those strands apart, or in order to read them for building proteins, you have to pull strands of DNA apart and then pack them back together again. So you need a strong bond, but not too strong. A covalent or an ionic bond would be too strong. If the bond wasn't strong enough, your strands would just come apart. It is the strength of the hydrogen bond that allows the DNA structure to exist and then be able to come apart as needed. So, very, very important bond type. Now, there are also other intermolecular forces, or one other one that we'll talk about, and we've actually already talked about this one before too. This one is the ion-dipole intermolecular force. Remember when we talked about how sodium ions are surrounded by water molecules? Water was polar, and the negative end of water surrounded the cations. Well, that was the ion-dipole intermolecular force causing that. And then we also talked about how the chloride ion would get surrounded by water molecules, but it would be the positive end of the polar molecule that would surround it. And because of, again, those intermolecular forces attracting it, ion to a dipole. So ion dipole, very important, especially when we talk about dissolving ionic compounds. Alright, so that's enough for this lecture. We've went through the types. What are intermolecular forces? We've talked about the different types of intermolecular forces. The next video, we'll come back and we'll talk about different physical properties. Besides, so far we've talked about boiling point, but we'll talk about different physical properties that all depend on the strength of intermolecular forces. Be back soon.